All right, chemistry, let's take a look at our video lecture, starting with Chapter 11, Section 3. After today's lecture, I want you to be able to explain how Gay-Lussac's law and Avogadro's law apply to the volumes of gases in chemical reactions. This is going to be very, very similar to what we did in the last set of lectures, where we started with the law of combining volumes of gas, but we are going to take that small, quick introduction and then move on to apply it and actually bring it into the field of stoichiometry. So yes, this is a stoichiometry section here, and we're going to use Gay-Lussac's law of combining volumes and Avogadro's law to help us do that with gases. Then I want you to be able to use a chemical equation to specify volume ratios for gaseous reactants or products, or both. We did that for our last quick write, where we used the coefficients of the balanced chemical equation to anticipate how many volumes were produced when a given number of volumes reacted. So we'll continue to do that and be a little bit more specific. And then use volume ratios, the ones that we just made, and the gas laws to calculate volumes, masses, or molar amounts, meaning the number of moles, of gaseous reactants or products. So here we go. In 1808, Joseph Gay-Lussac made an important discovery. If the pressure and temperature are kept constant, gases react in volume proportions that are small whole numbers. This is called Gay-Lussac's law of combining volumes. Gay-Lussac's law of combining volumes states that the volumes of gases involved in a chemical change can be represented by the ratio of small whole numbers. Again, I'm going to read that again. The volume of gases involved in a chemical change can be represented by small whole number ratios. That should seem very familiar, going all the way back to balancing chemical equations. Now, obviously, we introduced that just this last assessment cycle, but this is even older than that. Again, you've already heard of this law. It was in the last assessment cycle. We're just continuing to deal with this topic. For example, trying to give a picture to what we've been talking about, something that we can imagine in our mind, hydrogen molecules combine with chlorine molecules. Remember, those are diatomic molecules, Brinkelhoff. And so that's the hydrogen and the chlorine in there. So that's going to be H2, as we can see right here, H2, and then Cl2 are in a volume, a 1-to-1 volume ratio. When they react 1-to-1, they produce twice that volume of hydrogen chloride. So they had two separate volumes of gas reacting to form two volumes of gases.
Gay-Lussac's law of combining volumes of gases says that gaseous products and reactants have ratios that can be expressed as small whole numbers. So if, at a constant temperature and pressure, one volume of hydrogen gas reacts completely with one volume of chlorine gas to produce two volumes of hydrogen chloride gas, we know that the mole ratio of the reactants is 1-to-1. In the early 1800s, Joseph Gay-Lussac studied the relationship between the volumes of gases involved in chemical reactions. He found that one volume of hydrogen gas reacts with one volume of chlorine gas to form two volumes of hydrogen chloride gas. No matter what volume of gases he used, the ratio of hydrogen and chlorine remained the same.
Oh, too fast. So let's apply this idea that Gay-Lussac started to our stoichiometry, but now we can talk about stoichiometry of gases. So we have the ideal gas law, and the ideal gas law relates the amount of gaseous substances in terms of moles in with the other gas variables like pressure, volume, and temperature, the typical ones, right? Ideal gas law, PV PV is equal to nRT. Right, so once we have moles in there, we have the ideal gas law. The ideal gas, ideal gas law, can be used in calculations involving gases that react. Ratios of gases will be the same as the mole ratios of gases in balanced equations. Again, balanced chemical equations are the key to stoichiometry. They are also the key to relating volumes of gases. So being able to balance an equation, make sure that there's nothing on the left side that isn't on the right side or vice versa. Remember, we're trying to satisfy the law of conservation of mass here. Avogadro's law shows that the mole ratio of two gases at the same temperature and pressure is the same as the volume ratio of the two gases, right? Mole ratio is the same as the volume ratio. Because remember, Avogadro's law, the first one, right? At standard temperature and pressure, 1 mole of a gas takes up 22.41 liters. And so there's always going to be that same ratio no matter what gas it is. Now, this fact is going to greatly simplify the calculation of the volume of products or reactants in a chemical reaction involving gases. So as long as we can remember to use Avogadro's law to identify volumes as being the same as mole ratios, we can really get a head start on our stoichiometric calculations. For example, consider the following equation for the production of ammonia. So we have hydrogen gas reacting with nitrogen gas to form ammonia gas at a mole ratio of 3 to 1 to 2. Remember how we say that out loud, a 3 to 1 to 2 ratio. That means 3 liters of hydrogen gas are reacting with 1 liter of nitrogen gas to form 2 liters of NH3, and no hydrogen is left over and no nitrogen is left over. Now you might wonder, why are we saying 3 liters? I thought this was a molar coefficient. Yes, this is simply a ratio, right? This is simply a ratio. For every 3 hydrogens that react, 1 nitrogen is going to have to react and 2 ammonias are produced. So it's just a ratio. It's just a baseline. We can actually multiply all these numbers by some common multiple, and we could use that just as easily. But we're just using the smallest common denominator here. Now, if we know the number of moles of a gaseous substance, we can use the ideal gas law to calculate the volume of that gas. Right? If we know the number of moles in a gaseous substance, we can calculate everything else we need. Now, this is something that I made nice and big on your notes, so hopefully you could read it and use it. Oh, please use it. This is going to be one of the longest calculations that you do in this chapter. I could give you the mass of an unknown, right, in grams, mass of an unknown, and you're going to have to convert that into moles. Why are you going to have to convert it into moles? Because the only way that you can change what substance you're talking about, right? We're talking about the known here, and we want to get to the unknown, because that's what the question is going to ask you about, right? An unknown. So you give them the mass of the known, use the molar mass as a conversion factor to convert into moles of the known. Then you can use your mole ratio to go from moles of the known into moles of the unknown, right? And then once you have moles of the unknown, you can rearrange all this stuff to solve for whatever you want. The nice example here is volume, rearranging the ideal gas law to solve for volume. So let's give this a shot. I'm going to have you guys attempt this first, because your basic skills right now should be able to bring you along this path, even if you don't quite understand each step. You should be able to go through the motions at the very least. So you guys are going to attempt this on your own first. How many liters of hydrogen gas will be produced at 280.0 Kelvin and 96.0 kilopascals if 1.74 moles of sodium react with excess water, according to the following equation? So here's my mole ratio, 2 to 2 to 2 to 1. Here's also my volume ratio, 2 to 2 to 2 to 1. All right, so again, let's identify what the question has given us. It's given us a temperature, it's given us a pressure, it's given us an in value, an amount of moles of sodium, right? That's out here, this sodium right here. And it's reacting with the water, sorry. And we're being asked about how much hydrogen. So this is going to be a 2 to 1 ratio, a 2 to 1 ratio. So starting with the amount of moles of sodium that react If I go backwards, I went backwards too far. That's going to plunk us right into this spot here to start. So we're going to have to use the mole ratio of sodium to hydrogen to be in moles of hydrogen. Then we can use the ideal gas law rearranged in this form exactly to solve for the volume of that unknown, which in this case is hydrogen. So again, this is what we know. I'm going to please press pause now to attempt your calculation. All right, guys. So we have temperature, we have pressure, we have an R value, which is 8.314. Why is it 8.314 and not 0.0821? Because of the units for pressure right here. This sample problem is using units of kilopascals, so we have to use the R value that has kilopascals in the unit. So that R value is going to be 8.314. Now, first thing we have to do is we have to convert into the number of moles, right? Moles of sodium into moles of hydrogen. Once we have this, the number of moles of hydrogens, we can plug that into the ideal gas law and solve for the number of liters of hydrogen. So our first calculation is going to look something like this, right? We started with 1.74 moles of sodium, used the 2-to-1 mole ratio to convert into moles of hydrogen, and then we end up with 0.870 moles of hydrogen. So now we have this, right? Now we have this value right here, the molar amount. We're going to plug that into the ideal gas law and solve for volume. Again, rearrange the ideal gas law before you plug and chug. It's going to make things a lot easier on you. So rearranging the ideal gas law before you plug in your values is going to look like this. Volume is equal to nRT over pressure. And now we have to just make sure we have the correct values lined up. We have the amount of moles of hydrogen that we just calculated, the 0.870 moles, multiplied by the appropriate R value, all right, which is the value of 8.314 because of this kilopascals over here. Our temperature is in Kelvin. They gave us the temperature in Kelvin, so that's nice and easy. But if a temperature Celsius is given, make sure you convert that into kelvins, divide by 96 kilopascals, and we end up with 21.1 liters of hydrogen. All right, chemistry, that's going to do it for this section. I will see you next period.